In this video, we'll be looking at the structure of the atom as well as doing some isotope problems. So the first thing we want to do when we talk about what an atom is to talk about the different parts and the different pieces that are going to go into making up an atom. So this table looks at some of the subatomic particles, those much smaller than an atom pieces that go into making an individual atom. So this chart gives us an ability to compare and contrast the different parts of the atom. And there's three different particles that go into making up an atom. We can have protons, neutrons, and electrons. And we're going to compare these with respect to relative mass, relative charge, and finally the location of where you would find these different particles within an individual atom. So we're going to start with relative mass. Now, the reason why we're dealing with relative mass instead of the actual mass is because of the very, very small scale that we're operating on. We could write the actual mass of a proton in grams or kilograms or milligrams. It's just an incredibly small number because we're dealing with some of the smallest bits of matter imaginable. It's really tough to get any kind of physical meaning for those numbers. The numbers are too small to really deal with easily, and you can't really relate them to anything that you're accustomed to seeing because of this very, very small nature. So instead of doing the actual mass, what we do is we call it the relative mass. And what this does is this allows us to go down to that very, very small scale and be able to compare and contrast things without having to use these ridiculously small numbers that are very cumbersome. So we would say that the relative mass of a proton is 1 AMU. And what AMU is AMU is kind of a unit that gets us into this relative mass instead of an actual mass in something like grams. So AMU actually just stands for atomic mass unit. AMU for that. And that's just a way to get us down to this incredibly small scale without having to use ridiculous numbers. So we would say that a proton has a mass of 1 AMU. A neutron we're also going to list as 1 AMU. It's slightly heavier than a proton in actuality, but it's so close that we can still list it as AMUs. For an electron, we're going to list the relative mass of an electron as 0 AMUs. Now you see that that 0 is in quotes. It's not actually true. An electron does have a mass. We can figure out what its mass is. It's just that compared to a proton or a neutron, the electron's mass is so small that it really doesn't contribute anything to the overall mass. An electron's mass is about 1,000th the mass of a proton. It's so incredibly small, though, it's easiest just to ignore its mass contribution. It's not going to contribute anything compared to the much larger protons and neutrons. To kind of think about this in a scenario you might be a little bit more accustomed to seeing is imagine stepping on a scale. When you step on that scale, it's going to read out your weight. Now imagine that a small butterfly comes and lands on your shoulder. That small butterfly is not going to change the number you see on that scale because you are so much bigger and so much heavier than that very small butterfly. But does that butterfly have its own mass? Sure, it has mass. We could measure that mass. It's just that combined with your mass or combined with your weight, the butterfly doesn't really contribute anything to the total weight. The total weight of you and the butterfly is essentially just you because the butterfly's mass is so incredibly small. Same thing's happening here with the electrons, the protons, and the neutrons. The electron's mass is so much smaller compared to the proton or the neutron that it's not contributing anything to that total mass. Now, the same thing we just did with mass, we're going to do with charge. We're not going to talk about overall charge because, again, that gets us to using very small and crazy abstract numbers that we're just don't have a lot of meaning for. So we talk about relative charge. And this allows us to compare and contrast things such that we can see similarities and differences easily, again, without using those ridiculously small numbers. So we would say that the proton has a relative charge of +1. Neutrons do not have any charge. This 0 is not in quotes. It is 0. They are electrically neutral. And the electron has the same strength charge as a proton, but the opposite charge. So a proton is +1, an electron ends up being -1. The last thing that we're going to talk about for these subatomic particles is location. Where would you find these at? And for the protons and the neutrons, they're located in what we would call the nucleus. So protons and neutrons live in the nucleus. Electrons live outside the nucleus. So this chart is useful. It gives you a good idea of comparing and contrasting, seeing similarities and differences between these different particles. But what it doesn't do is it still doesn't give you a good picture of what an atom actually looks like. So that's what we need to look at next, is what do these atoms actually look like? So what do these atoms actually look like? You have probably seen at some point, either in a textbook or a previous science class, what we would call the classic model of an atom. That's kind of shown on the left with the picture. You know, you have a nucleus in the middle, and then everything surrounding it. It's almost the same model you would use in biology for a human cell. There's a problem with using this model for an atom. The problem with this model for the atom is it gets the proportions extremely wrong. It's not an accurate viewing of what an atom looks like. This type of model greatly over-exaggerates the volume of the nucleus. So it's not realistic. Even if you were to make the nucleus the smallest dot imaginable, even that would probably greatly over-exaggerate that volume of the nucleus. The nucleus is very, very, very tiny in terms of the volume, how much space it actually is taking up. So what I want you to do is to, instead of this kind of classic textbook model of an atom, I want to kind of use some things that you're probably familiar with in order to give you a better model of an atom. I want you to think about a different way of visualizing what an atom actually looks like. And in order to visualize this, I want you to think about two things that you've probably experienced. On the left, you see a picture of a large sports stadium. This one happens to be a baseball stadium. You can do a football stadium, a soccer stadium, a basketball stadium, but a large sports stadium. On the right, you see a picture of some peas. I want you to imagine taking one of those individual peas and walking out to the middle of that sports stadium and dropping that pea in the middle of the sports stadium. If you can visualize that, or doing that, you can think about how small the pea is compared to the rest of that sports stadium. That's your actual model of the atom. I want you to think about the pea as the nucleus. The rest of the atom would be the rest of that sports stadium. So you can see how incredibly tiny that nucleus is compared to the rest of that sports stadium. The nucleus is very, very small in volume. Meanwhile, compared to what the rest of the atom is. It takes up only a very, very minuscule amount of the volume of the atom. This gets you much closer to the actual proportions of what an atom looks like. The nucleus is incredibly tiny in terms of that volume. So if you can do that visualization, that gives you a better idea of the relative proportions of the nucleus versus the rest of the atom. The nucleus is incredibly small. Because of this, I want you to think about that P in that sports stadium as well, with the P being the nucleus and the entire rest of the stadium being that atom. You have two very, very different worlds set up when you compare inside and outside of the nucleus. I want to go through and do that comparison with you. So first, let's start with what's going on inside the nucleus. So inside the nucleus, we saw that we had protons and neutrons. Remember, those are the things that are contributing the mass. So I list a large mass here. Remember, we're at the tiniest scale, so it's not like a big anvil or something that weighs a lot, but on the scale we're at, that's where all of the mass is in the atom. It's in the nucleus. So it has all the mass located in the nucleus, but go back to that visualization of the P and the rest of the stadium. Remember, the nucleus is that P. So even though it has a very, very large mass, it has a very, very small volume associated with it. We kind of go back to something that we've talked about previously. We've talked about density. A large mass and a small volume makes things extremely dense. If we think about density being mass divided by our volume, well, if you have a very, very large mass and a very, very small volume, that is going to be extremely dense, incredibly dense, more dense than you can even possibly imagine. So to kind of give you an idea of how dense the actual nucleus of an atom is, what I want to do is I want to relate this to kind of something you're familiar with. Okay? You're familiar with a coin or a small piece of metal. You recognize those things as relatively dense. Of all the different types of matter you interact with, you know, that lead weight or that sinker is very dense. It has a lot of mass compared to the volume. The density of a nucleus, an individual nucleus, is millions to billions of times more dense than that densest material that you're used to dealing with and manipulating with here on our macroscopic scale. So when we say extremely dense, we mean extremely dense. What you're also going to find in the nucleus, we said protons and neutrons are in the nucleus. We know protons are positively charged. Neutrons are electrically neutral. So I have all of those protons with positive charge that are jammed into that very small space in the nucleus, that very small volume. If I start jamming a lot of positive charge into a very small space, I'm going to get an extremely concentrated positive charge. So when you think about the nucleus, I want you to think about extreme density, lots of mass, small volume, and a whole bunch of positive charge jammed into that one small space. If we compare what's happening inside the nucleus to what's happening outside the nucleus, we see we're going to get a very, very different world. Outside the nucleus, we just have the electrons. We saw that the electrons really don't contribute that much to the mass. We're going to get a very, very small mass out of that. But we have a very, very large volume. We have a lot of space available for that. Remember, this is the P and the baseball stadium. The entire baseball stadium is outside the nucleus, the rest of the atom that's not the nucleus. So small mass, large volume, that's going to mean the exact opposite of what we saw inside the nucleus. This is not dense at all. If we think about density being mass over volume again, if you have a very, very small mass, but a very, very large density, or sorry, you have a very, very small mass, but a very, very large volume. So small mass, large volume, that's not going to be dense at all. Very, very low density. Now, sure, we do have all of the negative charge located outside the nucleus, but remember, we have a very, very large volume. Being we have a very, very large volume, that negative charge gets spread out. So we would say this is a very diffuse or spread out negative charge outside the nucleus. So when you're looking at inside the nucleus versus outside the nucleus, when you're looking at that structure of the atom, you should be noticing you have very, very different worlds going on. Inside the nucleus, a lot of mass, almost no volume, very, very dense, very, very concentrated positive charge. Meanwhile, outside the nucleus, you have the electrons, not a lot of mass, a whole bunch of volume, no density at all, not dense at all. And that negative charge is very, very spread out because of that large volume that you have. What we want to do next is to make sure you're able to do isotope problems. So when we're doing isotope problems, there's a format, a systematized format for how we write isotopes. So I want to go through this format in very, very general terms, and then we're going to do some specific examples of how to actually do isotope problems. So everything has a specific location that it goes to. So in the middle, kind of where the big box is, that elemental symbol, that's the biggest part of that. And you're just using whatever elemental symbol for that element that you are dealing with. If you're dealing with nitrogen, you'd have a big N in this box. If you're dealing with carbon, you would have a big C in that box. If you're dealing with sodium, you would have an Na in that box. So that kind of tells you what element you are dealing with. In the upper left-hand corner is where the mass number is placed. So let's talk about what the mass number means. The mass number kind of means what it's hinting at. What is the mass of the isotope? Well, we can be a little bit more specific than that. If we look back to what we talked about previously in this presentation, we saw that of the three different parts of the atoms, protons, neutrons, and electrons, that the electrons really didn't contribute much to the mass, such that the mass number is really going to just be the sum total of everything that contributes to the mass. Well, the only thing that contributes to the mass are protons and neutrons. So our mass number is the number of protons plus the number of neutrons. In the lower left-hand corner, that's where you see the atomic number placed. So the atomic number gets at the identity of the element. Which element are you actually dealing with? One way of thinking about this is it's that element's social security number. We each have unique social security numbers. Every one of us has a different social security number. It's a unique identifier that relates to us. Well, for elements and isotopes, that unique identifier is the atomic number. Every different element will have its own atomic number. And what makes each element different from another element is the number of protons. The atomic number is going to equal the number of protons that you have in that specific atom. In the upper right-hand corner, something that you will sometimes see is a charge number. So for charge, kind of getting at what it's actually hinting it's getting at, this is the charge of the isotope. So what is that charge of the isotope? Now, atoms always start as neutral, as having the same number of protons and electrons. Remember, The neutrons don't contribute anything to the charge. So this charge number kind of shows you that balance between protons and electrons. Where are you at in that? So that gets calculated by kind of protons minus electrons will always give you that charge number. This charge number can change because, as we're going to see in this course, the electrons are the movers, are the doers of chemistry. They're the things that are changing. To kind of relate electrons to something you're a little bit more familiar with, I'm going to use a little bit of an economic example. If we were in an economics class, we'd be studying money. Where's money going to? What's changing with the money? The money is the currency. In chemistry, electrons are the currency. Anything you could say about money in an economic sense, you could say about electrons in a chemical sense. And let's just go through some examples of this. When it's your payday, you gain money that day. Well, atoms can gain electrons. When you're paying bills, you have a bill that comes due. Well, guess what? You're losing money that day, or you purchase something, you're losing money. Atoms can lose electrons. Remember, anything you can say about money in an economic way, you can say about electrons in a chemical way. Money can be gained, money can be lost, electrons can be gained, electrons can be lost. If you're married, your money is shared with your spouse. Electrons can be shared. Your money may be in different areas, different accounts. Electrons can be in different specific regions of the atom. Electrons are really the currency of chemistry. And what this charge number is really getting at is it's really getting at where do you stand. The protons aren't really going to change that much. It's the electrons that are the doers. So what this charge number tells us is where are we at in that very quick accounting balance of our relationship between protons and electrons. So I want to show a picture of the periodic table really quickly before we do some specific isotope problems. Now, the first thing you want to notice about this periodic table is the periodic table is not written in isotopic format. That format we just saw with the mass number in the upper left-hand corner, the atomic number in the bottom left-hand corner, the charge in the upper right. Periodic tables are not written in that isotopic format. And the reason being is that isotopic format deals with one specific isotope of that element. Meanwhile, the periodic table has to deal with all of the isotopes of that. So that's the first thing you want to notice. This periodic table that you're looking at, the atomic number is actually written in the upper left, because remember, we're not dealing with isotopic format here. So if I look at the atomic numbers, you see they're increasing left to right. Okay, 1, 2, 3, 4. They're increasing left to right. Remember, that atomic number, if we look at carbon, element 6, and in that upper right-hand area, I'm kind of coloring it in yellow right here. Carbon's atomic number is 6. What does that mean? That means every carbon atom in the universe has 6 protons in it. Remember, protons matches the atomic number. It's what makes carbon carbon. Every carbon will have 6 protons. If you have a number other than 6 protons, you are not carbon. You have to be something else. Every carbon will have 6 protons. If I look a little bit farther to the right, now I'm shading in element number 8 here, oxygen. Oxygen's atomic number is 8. Every single oxygen atom in the universe will have 8 protons in it. It's what makes oxygen oxygen. If you have 8 protons, you are oxygen. If you have a number other than 8, you can't be oxygen. You must be something else. We just go one more to the right. If I look at element number 9, shading that in, highlighting that in for us to look at. Fluorine. Fluorine's atomic number is 9. Every fluorine atom in the universe will have 9 protons in it. It is what makes fluorine fluorine. 9 protons is always going to give you fluorine. That's that identity element to it. That's that identity piece. That's that atom's social security number, that element's social security number that uniquely identifies that compared to all of the other ones. We want to start being able to use some of the different pieces that we just saw in order to actually solve problems. Because when you write out an isotope in that specific isotopic format, there's a lot of information encoded in there. We want to get a little bit of practice of pulling that information out. So our first kind of example of dealing with isotopes is we listed an isotope in its regular isotopic format. Now, based upon that, we are going to figure out the following. We're going to figure out the number of protons. We're going to figure out the number of neutrons. We're going to determine the number of electrons. We'll get the mass number in there. We'll get the atomic number in there. We'll get the charge number in there. All of that information is encoded into that correctly written isotopic format. So we want to work at extracting that information out. So we're going to start with the easiest pieces and then work towards the ones that require a little bit more analysis. So I'm going to skip the protons, neutrons, and electrons right now because that requires a little bit of work in order to get at. Let's start with the mass number. To get the mass number, you just have to recognize where is that mass number located when we write something in isotopic format. Well, when we write something in isotopic format, the mass number goes in that upper left-hand corner. So when we look at that isotope, what's that mass number? Well, that upper left-hand number is 31. That means our mass number is 31. Where's the atomic number located? Well, we know the atomic number is located in that lower left-hand corner. What do we see in that lower left-hand corner? 15. Well, that means our atomic number is 15. The charge, if there is a charge, we know is located in the upper right-hand corner. That's -3. Now, sometimes you'll see it written 3 minus, sometimes you'll see it written -3. It's the same information. It's kind of like first name, last name versus last name, first name. Whether you write your first name first and then your last name, or your last name and then your first name, it doesn't change your identity. You're still you. Whether you go first name, last name, or then last name, first name, kind of the same idea with the 3 minus and the -3. It doesn't ultimately matter. So now we got the mass number, the atomic number, and the charge. Now we can kind of do the work at figuring out the number of protons, the number of neutrons, and the number of electrons. So let's start with the number of protons. Well, how are we going to determine the number of protons? To determine the number of protons, we have to remember what the atomic number is. The atomic number matches the number of protons. These will always match. It's the definition of what the atomic number is. Your atomic number always has to match the number of protons. It really is what the atomic number is. It's the identity, and the identity is the number of protons that we have. Now, to figure out the number of neutrons. So we're going to work and figure out how many neutrons we actually have here. Well, how are we going to get at that information? Well, if you kind of go back a couple slides when we talked about what the mass number is, we said that the mass number was the contribution of everything that leads into mass. Remember, we said that the mass number really equaled the number of protons plus the number of neutrons. So now we just have to figure out what we're dealing with. We already knew what the mass number was. The mass number was 31. We already figured that out based upon its location. Well, we already figured out the number of protons as well. So the total mass is 31. 15 of that came from the protons. Where does the rest of it have to come from? The rest of it has to come from however many neutrons we actually have. So that's how we're going to determine that we're dealing with 16 neutrons in this. 31's the total. Take away what you already know, the 15 protons. What will you have left? That will be your number of neutrons, which is going to be 16. Now we're looking at figuring out how many electrons we have. Well, to determine the electrons, we're going to use what we knew about the charge. So we said that the charge, if you would go back a couple slides, you would see that the charge is our number of protons minus the number of electrons. So charge is protons minus electrons. Well, what's our charge? Well, we already know that. That's just knowing where that charge is located. It's located in the upper right-hand corner. That would be -3. We already determined how many protons we had. 15. So now we need to determine from that how many electrons will we ultimately have in this. And there's a couple different ways of going about it. You could kind of do the little algebra problem we have set up here. -3 equals 15 minus what? So 15 minus what gives you -3. You could determine that that's going to be 18. There's another way of doing it that's a little bit less mathematical, a little bit more chemical. Is here you have to recognize that the charge is that balance between the protons and the electrons. So the fact that you have a negative charge tells you you have more electrons than protons. That's what the negative part of that tells you. So you know you better have more than 15 electrons because you have 15 protons. And you know you have to have more electrons than protons. How many more electrons than protons? Well, that would be 3 more. Remember, the electrons are contributing that negative charge. The protons are contributing the positive charge. So if your total is negative, that means you better have more electrons than protons. That's the case we're looking for here. So we're going to have 18 electrons, 3 more electrons than protons to make that work. So this is how you can extract this type of information off of something written in its isotopic designation. So we want to do another one. What I would suggest you do is actually pause the video, try this one on by yourselves. So pause the video right now. Try this one on your own. After you think what you have is correct, resume the video and see if you did it in the correct way. So highly recommend you pause the video, try this yourself, and then see if you did this correctly. Now, did you do this correctly? Well, let's take a look at how we're going to do this. I'm going to do this the same way as the previous one and take out the easy ones first. The easiest ones are mass number, atomic number, and charge. Reason being, that's just knowing where those things are located. Mass number is always in the upper left-hand corner. So the mass number there will be 44. The atomic number is always in the lower left-hand corner. That will be 20. Our charge, +2 or 2+, that's in the upper right-hand corner. So we kind of took care of that right away. Now we can kind of get at our protons, neutrons, and electrons. Well, how are we going to get our number of protons? Well, our number of protons is going to be 20. Remember how we determined that. Your number of protons has to match what your atomic number is. Always, always, always. That's the definition. Well, now how are we going to get at the number of neutrons? Well, to get at the number of neutrons, we need to know we're going to use what we know about the mass number. Mass number is going to be protons plus neutrons. Well, what's our total mass number? Our total mass number is 44. How many protons do we have? Well, we already have 20, so of those 44 total mass units, 20 of them come from the protons. That means the rest of them had better come from the neutrons. That's going to give us our total of 24 neutrons. 24 plus 20 would give us our 44 total for that mass number. So you take 44, subtract off what you already know, the 20 protons. The rest of it has to be your amount of neutrons. Lastly, we're looking at the electrons. Well, how can we figure out the number of electrons? Well, we would have our charge. We know that our charge is going to be protons minus electrons. So what's our charge? Our charge is plus 2. 2 plus, doesn't matter how you write it. How many protons do we have? We have 20. What's going to be the missing piece? The missing piece is going to be our amount of electrons. You can solve the little algebra problem. 20 minus what gives you positive 2? Well, that would be 18. Or you can kind of think about it a little bit more chemically. Protons are positively charged, electrons are negatively charged. Well, what's my net charge? My net charge is positive, so I better have more protons than electrons. My number of electrons have to be less than my number of protons. How much less? Well, 2 less. So that's kind of how you go through and extract that information out of these isotopic designations. So in this example is really kind of the opposite of the previous examples that we did. Here, we're going to complete the information kind of in the table and then write out that standard isotopic designation that we're seeing in this. Okay? So first, we're going to complete the table. So we would be given all the numbers in black, and we would have to fill in the missing pieces. So the missing pieces here are protons and our charge. So how are we going to get at the number of protons? Well, the easiest way would be to remember that the atomic number and the number of protons have to match. That's the definition of what the atomic number is, and that would give us 16 protons. You could figure out the number of protons a different way. You could use the mass number and the number of neutrons to figure out the number of protons as well. So let's go for the charge. Remember, our charge is our balance between our protons and our electrons. We have 2 more electrons than protons, so that would be a -2 charge. So now we finished off what's in the table. Now what we want to do is we want to be able to write this out in its standard isotopic format. So standard isotopic format, we would have the mass number in that upper left-hand corner. That would be 34. In the lower left-hand corner would be our atomic number, 16. In the upper right-hand corner, we would have the charge. That would be -2 or 2-. What we're missing here is the elemental symbol. So how are we going to figure out that elemental symbol? So for this, you would have to look at a periodic table. And remember, find that atomic number 16. Which element is number 16? Remember, we have to do identity based off of atomic number. Do not try to do identity off of mass numbers, because mass numbers can change and vary. Atomic numbers can't. That's our identity piece. So when you look at a periodic table, you would see element number 16 is sulfur. We would have S as our symbol in here. So that's kind of how to go the opposite way in terms of writing out these isotopes for yourself based upon information for protons, neutrons, electrons. So we've used the term isotope quite a bit, but we haven't actually formally, defined it yet. So what is an isotope? Well, an isotope is a form or a version of the same element, but with different mass numbers. So if we want to think about how can we have the same element with different mass numbers, well, that's going to result from a differing number of neutrons. When we think about that, has to be true. If we have the same element, the number of protons is the same. And if the number of protons is the same, but we have different masses, those different masses have to come from a differing number of neutrons. So I kind of wanted to show what's going on with this in this table. So across the top, I put 3 different isotopes: carbon-12, carbon-13, carbon-14. So what you notice is the atomic numbers aren't listed on these. And that's not, trying to put one over on you or be tricky. You'll see all the different textbooks do this as well. It's generally assumed that if you're doing chemistry, well, you're going to have a periodic table available to look at. So you don't actually have to put the atomic number in necessarily, because you could just use the periodic table to look up carbon and say, oh, carbon-6 is kind of already in there. The other thing that you're not seeing necessarily is the charge in that upper right-hand corner. Well, generally, if something is 0 in chemistry, instead of writing a 0, we just leave it blank. So that means our charge is 0 for each one of these. So you'll often see things written that way as well. So for each one of these isotopes, for carbon-12, if I kind of go down this first column, how many protons? Well, every carbon will have 6 protons. To get up to a total mass of 12, it better have 6 neutrons. And being there's no charge, our electrons and protons have to match. If I compare that to carbon-13, carbon-13 will still have 6 protons. It has to. But to get up to a mass of carbon-13, we would have to have 7 neutrons. Still 6 electrons, because there is no charge. Electrons and protons would have to match. All the way on the right, it's still carbon, so it better have 6 protons, but to get up to a mass of 14, I would need 8 neutrons. Our number of electrons is 6, no charge. That means protons and electrons have to match again. So you can see in these different isotopes of carbon, the only difference is in how many neutrons we actually have. The very last row has the relative abundance. So how often are you likely to find that specific isotope? And most of the carbon that we run across, about 99% of it, is carbon-12. About 1% of it is carbon-13, and then there is a small trace amount of carbon-14. So now we have to relate some of this work that we've done with these isotopes back to what we've been seeing on the periodic table. When you look at carbon on a periodic table, kind of showed this here, this is kind of what you're looking at. And you see that 12.011. What that 12.011 represents is the weighted average of all of the carbon isotopes, all of the isotopes of carbon. Now that 12.011 What that says is that's the weighted average. There is zero, none, absolutely none. There are no carbon atoms in the universe that have a weight of 12.011. None of them. What that 12.011 is that's the weighted average of carbon 12, carbon 13, and carbon 14. It's so close to 12 because most of it, about 99% of it, is carbon 12. Why is it a little bit over 12? Because we have a tiny, tiny amount of carbon 13 and carbon 14. So when you look at the periodic table, you're not looking at the mass of a specific isotope. What you're looking at when you see that mass on the periodic table is you're looking at the weighted average of all of those isotopes with their relative abundance already factored in. Okay. That's the average. Remember, there are no carbon atoms that weigh 12.011. None of them. They can't. You can't have part of a proton or part of a neutron. Carbon either weighs 12, 13, or 14. The 12.011 is that weighted average. And again, it's so close to 12 because most of the carbon has a mass of 12, but a small amount of it, a little bit of carbon 13, a little bit of carbon 14, bump that average up slightly. Big take-home lesson to this is that there's a directionality to this. The relative abundance information, so the information in the table, can tell you the average, but it doesn't work backwards. Just knowing the weighted average does not allow you to accurately predict what specific isotopes there are or what their abundances will be. So just knowing that carbon, if you just had carbon's average is 12.011, you wouldn't necessarily know the abundance of carbon 12, carbon 13, carbon 14, or even if there was necessarily a carbon 14 or 13. And to kind of show this, I want to do a little bit of a relationship to this with something that you're a little bit more familiar with. And what you're a lot more familiar with than isotopes are your grades. In a class, if you get a final average of 83.3%, well, that doesn't mean you got any individual grade of 83.3%. That's your weighted average of all your papers, quizzes, exams, projects. If someone told you, well, my final average was 83.3%, that doesn't tell you how well they did on any specific quiz, exam, paper, or project. All it does is tell you overall, with everything averaged together, what was that final average. Another way of thinking of it is, let's say you and your friend both end up with a 94.4 final average. Congratulations, that's a really good average. But can two people in a class have the same final average but go about it very, very different ways? Just because the final average was the same, does that mean those individuals scored identically on every single project, paper, assignment, quiz, exam? No, they probably went about it a little bit different ways. That's that directionality piece. Just knowing the final average doesn't tell you what the actual pieces were. But if you know all of the pieces, you could determine that final average. If you had all the quiz, exam, paper, project scores, you could figure out that final average, but you can't work backwards. That same directionality that you're familiar with in your grades, that's working here for, the isotopes, which are like the individual assignments, individual quizzes, exams. And then what you're looking at the periodic table is that final weighted average.